نحن في سكيلز بيت الخبرة ملتزمون بالجيمات الثلاث: جديد، جيد، جدوى.
Number one, we have longitudinal vibration. And we had the structure like this, viscoelastic. Constraining layer. The basic structure is oscillating at constant strain. Then H1, this is the constraining layer. And the viscoelastic material. And put the coordinate system in the middle of the constraining layer. We wrote down the equation of motion, and we neglected the inertia of the constraining layer, and we call this equation of static or quasi-static equilibrium. For this, we found that we have B asterisk squared uxx minus u is equal to minus epsilon 0 and x, where the B asterisk squared is h1, h2, e2. We start. We said this is second order differential equation, has two boundary conditions. At x is equal to plus or minus L over 2, epsilon is equal to 0 for partial u by partial x or u of x. Okay. For this arrangement, we had something like this. The structure, the base structure expands with epsilon 0. And the top expands with different displacement, the viscoelastic material shears like this. And we found the shear in terms of the deflection U0 and the deflection U. The difference between them were the shear angle gamma. Okay. Now let's repeat this again like this. This expands. I'm going to take this signal and feed it back to the top layer, if the top layer is active material. And I'm going to make the top layer shrink. So instead of having this angle, I'll have much bigger angle. So now I'm going to take this signal, put here a controller, and then take this output and feed it to the top layer, which was originally like this. And if this is piezoelectric material, I'm going to make it shrink, so it will be like this. This is by feeding the signal back to the piezo. The result is, instead of shear angle this much, I'm going to increase the shear angle to this much. So the yellow line is the passive case. And if I come and instead of the constraining layer, which is, we said piece of aluminum, I'm going to make it piece of piezoelectric material. So when I take the measurement of the expansion here and send it negative feedback, the top shrinks, then I increase the shear angle. If the reverse happens, if this shrinks, then I take the signal, feed it negatively back, so it will be positive, it'll expand, and have much bigger shear angle also. The difference between these two cases, here, there's no force. Partial U by partial X is equal to 0. At here and at here. Okay? In this case, partial U by partial X is whatever strain I put by the piezoelectric material. So this would be epsilon piezo. Now, for this case, this is passive. Constrained layer, damping, or the acronym PCLD. Here is exactly the same. Instead of passive constrained layer, I put active component. So this is an active piezo material. And this would be active constrained layer damping or ACLD. Now, this exactly the same equation for the two cases. The only difference will be in the boundary condition. I solved this in great detail. We have now here second order differential equation. Solve for U. We have U. We have U0. From the two we get the shear angle. From the shear angle, I can get the energy dissipation, I can get the loss factor. So for the first case, we solve for U. And then determine gamma. And then compute the energy dissipation. And if you remember, this was equal to pi eta J prime H2 gamma squared. Okay? And then compute the total W, which is the integral of del W dx, and then put it in a dimensionless form. And we end up with the loss factor equation. So this was the solution procedure. Okay, now for this case, it's exactly the same. I can repeat everything. I'll end up for active constraint layer, damping, my eta will be made of two components. Eta passive plus eta because of the active component. Okay. Now the nice thing here is, now if this system, the controller fails, your system still has fail-safe net because of the passive damping. Okay? So who will do this calculation? So the first problem is exactly what I outlined on the board here. We have to calculate the solution for this case, and then now in terms of the epsilon p. Now epsilon p, I did not include it in this homework problem. I can generate epsilon p is equal to minus some control gain epsilon 0. For example, this control gain can be either real or can be a complex number. So I can put velocity delay, for example. So this can be minus k proportional, k derivative d by dt of epsilon 0. Okay, so I can have proportional and derivative, for example. Okay, but in this homework problem, we don't have any control effect. Just the epsilon p is a constant that you can generate by yourself. Okay, second part, the second problem needs some description that we will do now. But before I do it, I want to just add a couple notes. some notes. If I have k is equal to k prime 1 plus eta I, then the force that I generate by this viscoelastic spring is equal to, and this is equal to and if x is equal to some x0 e to the I omega t, then x dot will equal to I omega x0 e to the I omega t and then now this group of terms is nothing but the x. Okay, so this is equal to, so now I can, for this case, replace I omega x by x dot. So now I can come here and write this equation again. F is equal to k prime x plus, and I'll replace I x by x dot over omega. X dot. Now we have here the force is made of two components, force elastic plus force damping. Now the energy dissipated is equal to integral fd dx. And then now I'm going to do it like this. Divide by dt, multiply by delta t. So now the integral, instead of on the stroke of travel, will be on the time of travel. And I'm going to get this in one cycle. Energy dissipated per one cycle. So this will be from 0 to 2 pi over omega. Now we come, replace Fd from here. Fd is k bar eta over omega and x dot. X dot, so I have x dot squared dt. Now we have, for example, x is equal to x0 sine omega t, then x dot will be omega x0 cosine omega t. And then I plug them here, then the energy per cycle, and this is, this is the dissipated energy. And I'm going to call this W. So this will equal to integral from 0 to 2 pi over omega, k prime eta over omega, and then the x dot squared, I'll replace it by omega squared, x0 squared, cosine squared, dt. Now integrate. The one of the omegas will cancel with one of the omega. I'll have k bar eta omega x naught squared. And then the cosine squared between the limit will be the limit over 2. So this would be times 2 pi over 2 omega. So the 2 will cancel with the 2. The omega will cancel with the omega. And this will equal to which is what we have here. Which is what we have here. This I have the width, so I put the width of the material in it. Okay? Now one more thing. This is the energy dissipated. What is the energy in the spring? So the potential energy this will equal to the spring is K and X, so the energy will be 1/2 x0 squared. So from here I have W is equal to pi W elastic is equal to 1/2 K x0 squared. Now I want to get this in a cycle. So we'll do the same, and then this would be here 1/2 K 0 squared, then W over WE is equal to pi x squared, and this will cancel over 2. And then now eta 2 pi, I'm sorry. Then eta will equal to W over WE. This ratio, the reason I'm saying this is the paper that I gave you reference to it last time, which is Plunkett and Lee. When you extend it to the bending case, he defines it like this, directly, without any reference. So now you will know why this we have this term 2 pi. But anyway, you could see in many vibration books, the ratio here is used as indication of the damping, but it's called a different name. This ratio is called the specific damping capacity. Specific damping capacity. I want to add one more thing. All this note is on a spring that has viscoelastic damping. So let's just say we have only viscous damping. So my F damping is equal to coefficient of damping x dot. Okay? And unfortunately we erased the part now where I want to determine the dissipated energy. So this will equal to the integral of FD dx, or FD, which is Cx dot, and dx, I'll divide it by delta t and multiply times delta t, so this would be x dot dt, and this will equal to C integral of x dot squared. We have omega squared, x0 squared, integral of cosine squared omega t dt. So this will equal to the limit over 2. So this will equal to the limit over 2 okay. So now here pi c omega x0 squared. For viscous damping, the energy dissipated depends on the frequency. For viscous damping, for viscoelastic damping, the energy dissipated does not depend on the frequency. Does not depend on the frequency. Okay, let's see one more thing which is very important. I'm gonna say my viscoelastic material, I want to represent it as if it is a viscous material. As if it is viscous material. So I'm going to get the equivalent viscous damping to a viscoelastic material. And I'll do this by just equating these two equations. So I'll have K prime eta x squared 0 pi will equal to pi c omega x squared, or this will mean like this. I'll equate the energy dissipated in the two cases. So the pi x squared will cancel out. And this says here that the C equivalent is equal to K prime eta over omega. I'm going to do one more step. I'm going to take this and divide it by C critical to evaluate the damping ratio. C is right here. K prime eta over omega. Cc, if you remember from vibration, is equal to 2 square root of K M. And I'm going to make this K prime. So this will equal to eta, and I'll put the 2 here. And this K prime will cancel with one of these, and this will be the square root of K prime over M, and then omega. So if I am at resonance, this ratio is equal to 1. It's equal to 1. And this, we have to keep this in our head very clearly, because many people confuse this. Eta, twice that. So if you have a viscoelastic material and they give you a loss factor, I have to divide this by 2 to get the equivalent damping ratio. The two are not equal. The two are not equal. If I get viscoelastic material, it is 1 loss factor. This is equivalent to damping ratio of 50%. Okay? So now from what I've done here, you could see where this form for the energy dissipation, Y in Plunkett and Lee, he has 2 pi in the denominator. If you look in Thomson book, for example, vibration, you will see he's using the specific damping capacity. And they use this quite a bit in composite material damping. Material that have fibers, they use this specific damping capacity. Okay. Now we're ready to continue last lecture, the last part of last lecture. All this was done on longitudinal vibration. Now we're going to go into transverse vibration. I did the last lecture, the 3-layer composite. And so this is H1, H2, and H3. This is the constraining layer. The bottom is our base structure. And then from the geometry, we found the kinematic equation that relates the shear angle to the longitudinal deflection in the top and bottom layer, as well as the slope of the deflection line. H2 is the thickness of the viscoelastic material, and then H is this distance. And H is equal to H1, H3 over 2 plus H2. And U3 is the longitudinal deflection of the base structure. U1 of the constraining layer. Now I'm going to take first a very simple case where U3 is almost zero. The pitch structure is massive compared to the rest of this thing, so U3 is equal to 0. So let's say here, consider this case. And then after we solve it, we'll do the case when U3 is not equal to 0. So this automatically says that gamma is equal to U1, and then here multiply by H2, HWX, and U1 will equal to H gamma minus HWX, and U1 partial with respect to X will equal to H2 gamma partial X, WX, and X. Now, for this case, if this moves U1, and this doesn't move, then I have something like this. Then the shear angle is right here, gamma. And I can get the shear angle in terms of the deflection and the slope of the deflection curve. Now, we can also look at forces generated to do this extension and the resistance that comes from the shear of the viscoelastic material. So now the force on top layer this will equal to E1 H1 times the width, and I'm going to do this force per unit width. So the Young modulus times the area times the strain U1. This times this would be the stress times the area of the cross section H1 and the unit width. This would be the force. So this is my H1, and I'm taking unit width perpendicular to the board. And the extension the rate of change of this force is counterbalanced by the deflection, by the shear stress. So now I can E1 H1 U1 XX will equal to G and gamma. the shear stress. Let's call this equation 1, and then this is equation 2. So now I'm going to replace the uxx from here, I'll differentiate the top again. So I'll have h u1xx is equal to h2 gamma xx minus h w1, 2, 3, and this will equal to g stricken gamma. And then we clean this equation, we'll have gamma xx will equal to minus g E1, H1, H2, and then gamma will equal to H over H2, W1, 2, 3. I'm gonna just, for simplicity, let P1 is equal to E1, H1, and this would be the longitudinal rigidity. So then we have gamma xx minus g asterisk k1 h2 gamma will equal to h 1, 2, 3. And then look here at a little note. We'll say here consider bending and a beam. The flexural rigidity, EI, I'm going to reduce it to this symbol. If the beam that we have has damping, so this is complex number, so this is a complex number. So I can write this as D multiplied times 1 plus eta and I. Now the equation of motion of a beam is EI or D W1, 2, 3, 4 plus M omega squared W is equal to 0, inertia term, or W1, 2, 3, 4 plus M omega squared over D T asterisk W is equal to 0, or W1, 2, 3, 4 plus the wave number to the 4th power, W is equal to 0. where KB is the bending wave number. Now this problem has four solutions. 2 propagating and 2 decaying. The propagating, one of them will be like this. W will equal to W0 e to the, I'm going to select one of them that has the following. I omega t minus k b and x. Okay? That's one of the propagating solutions. But this k b is equal to omega to the 1/2 divided by d t over m and the d is complex number, is right here. I'm going to replace this from here. Is d t to the 4th power, to the 1/4 power. And this we can reduce it to this number is the real wave number multiplied times 1 minus eta over 4 I, approximately 1 over eta over 4 I. Now this is k, I'm sorry, kb. This should be complex number here, and this is complex number here. So this now has real wave number and decaying part. Now my solution this solution, I'm going to replace k asterisk from here. Then now W will equal to W0 e to the I omega t, and then minus what we have here is minus k b, which will be minus k b plus kbx plus k b eta over 4 and I. Okay, so now this will equal to W0 e to the I omega t minus kb x e to the I, I'm sorry, to the minus kb eta over 4.
Should be an X.
Pardon?
Should be an X.
X, I'm sorry. And this whole thing, I'm going to just call it any other name like W0 prime e to the minus k b over 4 eta times x. The energy, we know it's equal to, for all the cases that we looked at, viscous damping or viscoelastic, equal some number times x squared, the amplitude squared. So this will equal to some number w squared. So this will equal to some number w0 squared e to the minus k b eta over 4. I'm sorry, over 2 because it's squared. Next. Now let's take the D energy by dx. So this will equal to C W0 squared. The derivative of this term is equal to e to the minus k b eta x over 2 times k b eta over 2 and minus. Now I'm going to look at D energy per dx. That's the rate of change of the energy divided by the energy. If I take this and divide it by this, so the result will equal to, this will cancel with this, this will cancel with this, this will cancel with this. The only term that remains is here, is beta over 2. Now, all this says, I can now determine the loss factor, and this will equal to 2 over k b times this ratio. So now we have this system, and this system is represented by this equation, and this equation gives us the shear angle as function of the transverse deflection. Transverse deflection, we have it in this form. So I can put this here, and for any position x, I can solve this differential equation. I determine the shear angle. We have the shear angle, we know how to determine this number from last lecture, pi g prime eta gamma squared. I know this number. We have the energy, we'll do it in 1 minute. We can calculate the loss factor for this system. This is all energy based. all energy-based analysis. So we can determine the equivalent loss factor for the system, and I'm going to put this C for the constrained layer assembly. Okay, now this number we have the equation here. Let me just say now the solution for eta C. Put W is equal to this W0 e to the I omega t minus k asterisk B and X. Solve gamma XX minus for gamma. And then calculate d energy by dx, which is pi g prime eta viscoelastic h2 gamma squared. Okay, and this using solution given. I'm going to do the solution, but if you want to take reference, that's the reference. Given in Eric Kerwin, damping, flexural wave by constrained layer this is Journal of Acoustic Society. America. And it is volume 31, number 7, page 952, 962, 1959. This is the first paper on this subject. I'm going to solve for gamma today, and then we'll continue next time. So now we'll take the W and replace it here, and then it will be partial differential equation in terms of gamma. We'll solve for gamma. Then the W, we have the W, then WXX will equal to, I'll differentiate this 3 times. So we'll have minus I, KB, and I'm going to leave it KB as it is, complex number, and then W0, E to the minus I, KBX, E to the I, omega t, and of course, this large last number is the original W. So this will be equal to minus I and W. Unplug it here now. Then we have minus G prime K1 H2 and gamma will equal to H over H2 and then minus K B Q I and W is 0. This equation has solution. Gamma will equal to IH KB W0 over H2 1 plus G over KB squared K1 and H2. Of course, this is a solution because if I take this and plug it here, it will satisfy this equation. Okay. Now the rest is all straightforward. We have the gamma expression like what we had before, and then get the energy equation, and then we plug in the loss factor and we get the loss factor. So I'll stop here. This is where we are for next lecture. And you can check here to see if it satisfies the equation. Yes, sir.
Why is that W0 equation instead of W?
W. I'm sorry, W.
What is W?
This paper is fantastic. It has a lot of meat. So please, if you can get it, it would be a fantastic thing to have. And then maybe I'll delay the homework till this was next Tuesday, so we'll make it Thursday. So make the date for the homework 26, 4/26. Because I did not cover all the material that I wanted to cover today. Okay, have a good evening and we'll see you on Thursday. Axis, so you have to get the neutral axis by the rules of bending, where the stress is equal to 0 at this neutral axis. So we will continue this constraint layer, and hopefully we'll wrap it up today. Now, what we done last lecture, we're looking at the main objective is trying to get the loss factor for a constrained layer damping in transverse vibration. And to do this, we did a couple things. Number one, we looked first at some definitions. We said we have a specific, let me write it down. Damping capacity. And this is equal to the dissipated energy divided by the total energy. For example, in the case of the spring mass system, we showed that this is the elastic energy that we put in the spring, or we store in the spring. Then we found the loss factor. Is equal to WD over 2 pi and W. And number 2, for a beam in bending, we wrote down the equation of motion. And we had the D is the flexural rigidity, and it has complex number, notation. And then mass per unit length and frequency. We said where the dt, I can write it down as dt, 1 plus, and and this comes from, like this is in conventional cases is equal to EI. Young modulus is complex number because of the viscoelastic material, so we have this loss factor in the picture. And then from here we solve for the propagating solution only. found that this is equal to and the KB is the wave number. And the wave number, we can get it from here, is equal to m omega squared dt asterisk under the fourth square to the fourth power. Okay. Now this KD will also has the complex effect of the loss factor, but it is in the denominator. So now we can substitute here is the dt, and we'll end up with the square root of m omega squared over d t, and then the remaining part, and this will be, as we did last time, 1 minus 1/4 eta and I. And this will be just a wave number for a plane beam without any losses, without any loss. This, I'm sorry, not the plane beam, the composite beam without the losses effect. So this is the wave number of the 3-layer beam, or the constraining layer assembly without losses. And then I'm multiplying it times 1 minus 1/4 eta and I. And then now I can take this and plug it here. So we'll end up with W is equal to W0 e to the I omega t minus k b asterisk s, and then e to the k b eta over 4 and x. So I'll substitute this in here. We have I here, and then I here, so it will be I squared minus, and then minus becomes plus, and this will be this term. And then now we said the energy is proportional to the deflection amplitude squared, the deflection squared. So now I can replace everything from here and plug it for the W. So this will equal to C W 0 e to the I omega t minus k b and x. And then here we'll have E k b eta over 2 and x. And I'll just make this whole thing as a constant, a new constant. And then now we said if I take this and get the derivative of this energy with respect to x, and divide it by the energy, then this will equal to, when I take this derivative, so this will be C prime, and then E k b eta over 2 and x times k b eta over 2, and then the denominator, the energy, is everything here. which is the C bar times this. So these two brackets will cancel out, and this will equal to KB eta over 2. So now the summary of all this, number 3, if I want to calculate the loss factor of an assembly of the constrained layer damping, then I'll rearrange this equation. I'll get eta here, and this will equal to 2 over KB d energy by dx divided by the energy. Okay, the number 4 that we did, and I said here just if U3 is equal to 0. Let me just define what these are first. For 3-layer constrained layer damping, this is the constrained layer, constraining layer. One, and then this is the viscoelastic material. 2, and then the base structure is 3. And this moves U1, this moves U2, U3, I'm sorry. And then the entire assembly moves in the transverse direction, W, and as a result, the viscoelastic material shears at an angle gamma. So these are the parameters that we have. We wrote down the geometry. We wrote down that gamma will equal to U1 minus U3 over H2, H over H2, Wx. And and this would be H1, H2, and H3. The thickness of each layer. And H is equal to H1 plus H3 over 2 plus H2. And we started looking at the first case if U3 is equal to 0. So if the base structure is very big, so it will not elastically deform in the longitudinal direction, but it will move in the transverse direction. This is very thin, so it will have longitudinal as well as bending. So if this is the case, then this term will drop out, and then gamma will equal to U1 over H2, H over H2. And from here, I can extract U1 will equal to H2 gamma minus H and Wx. And from this, then I can say that if I differentiate this twice with respect to x, partially with respect to x, one, two, three. And then now we'll say we have equilibrium, again quasi-static equilibrium. When the load acting on the top layer is counterbalanced by the shear and the viscoelastic layer. So now here the longitudinal load on layer 1 is equal to the shear load. Of course, because it expands from the two directions, then we'll take the difference between these two is counterbalanced by the shear, as if we're doing the free body diagram for this. So like if I take the top layer like this, for example, then this is the shear on the viscoelastic layer. Then I have here stress, and this is dx. And then I have here sigma 1 plus sigma 1, partial sigma 1 by partial x dx. Then the two counterbalance each other, and we have partial sigma 1 by partial x times dx is equal to the shear stress and these are stresses, so I have to convert them to forces to have equilibrium. So the force here is acting on this little area, which is H1 and B, perpendicular. The shear stress is acting on dx and b. So now this will cancel with this. This will cancel with this, and we'll have the shear stress, which is G gamma, is equal to H1. The partial is equal to Young's modulus of the top layer times the strain derivative of the strain, or this will be, write it down like this. So this will be partial by partial x of Young's modulus U1 x. And I'll take the E1 outside, so I have E1 H1 partial U1 with respect to x, so this will be U1 xx and gamma. Now this term we have it from the geometry here. So now I can replace it from this equation. So this is equal to E1 H1 and then we have H2 gamma XX minus HW1, 2, 3 will equal to G asterisk and gamma. And then now we clean this equation. So we'll have E1 H1 H2 divided by G G asterisk minus E1 H1 H over G asterisk W 1, 2, 3 is equal to gamma. We need that. So we have here. Now from this I'll have gamma XX. Then bring the gamma here, so we'll have G is equal to H over H2, W1, 2, and 3. And for just simplicity, we'll just say here let E1, H1 is equal to K1. So gamma XX now we'll say let W is equal to W0 e to the I omega t minus asterisk. And plug it here. Okay, so this will give us W 1, 2, 3 will equal to this whole thing as it is. And then the derivatives 3 times with respect to x. So I'll have I, K, B 3 times, and all of them are minuses. So we'll have 1 minus, 1, we'll have minus I, K, B, asterisk, cubed. And this is exactly like this. So this will be W, and then we have here K, B, asterisk, cubed. Minus and minus becomes plus, and we have what we have here. Now I don't need also this. Then the equation gamma XX minus G prime K1H2 and gamma H over H2 KB cubed. We should have 1 I here, huh? So we have so the 2 I's will give us negative, positive, and then we have negatives should be negative. Okay. So this should be like this. And then
Positive.
it's positive.
Squared I is negative.
Okay, yeah. I, and then W. So this equation has a solution. Gamma, and I gave you the equation for gamma last time. Equal to I, H, KB, divided by H2, 1 plus G asterisk KB squared K1 H2 times W. And this is a solution for this equation, because if you take it and plug it in this equation, it will satisfy it. So just say check that solution gamma satisfies the differential equation. Now we have the gamma. I need two pieces of information. This energy per unit length and the energy, so I can calculate the loss factor. So now we can calculate this term from the previous lectures, the energy dissipation per unit length. This is equal to gamma squared G prime eta times the H2 and pi. So so now we have the gamma expression, and this is eta of the viscoelastic material. And the eta that we're looking for is of the entire assembly. Okay, now we need the energy. So this energy I have W, we wrote it as W0 e to the I omega t minus k bnx. I can take the real part of this and I write this W0 sine omega t minus, and I'll just make it KB, but this is complex number, okay? Times the x. Now I can get the velocity. So this will equal to and I can also get the angular velocity. So the angular velocity will equal to minus W0 omega KB sine. So now sine minus minus will be plus. So this is linear velocity. And this is angular velocity. Let's get the WXX. WXX will be differential of this minus KB W0 cosine and WXX will be minus minus will be plus, and then this will stay as it is, so this will be KB squared sine from here I can get the moment. And the moment will equal to dt w xx. So this will equal to minus dt kb w0 sine omega t minus k bnx. Now I can get the shear, and the shear will equal to the force F. This will be minus partial m by partial x, and this will be d t asterisk. We have minus here and minus, so this will be also minus kb cube dnx. So now for this total energy, I'll get it in two steps. I'll get first the power, and the power will equal to the force times the velocity plus the moment times partial x. So this is power, and after we get the power, we'll multiply it by the period so we can get the energy per unit cycle. So this times this times this will be cosine squared, and then we have w 0 omega, and then here we have w0, so this would be w squared k cubed, and dt cosine squared, and then we have minus here. Plus the moment times the velocity, we have dt kb squared, and then w0 times this, which is w0 again, so this will be w0 squared, and then we have omega. We have one more kb, so this would be kb cubed, and then we have sine here, so this is sine squared. So now, if you look at this term and this term, they are exactly the same, and I'll factor them out, and I have sine squared plus cosine squared is equal to 1. So this will equal to w0 squared omega kb squared and dt. So now the energy will equal to the power times the period. The period is 2 pi over omega. So now this will equal to w0 squared. Let me do it like this. w0 squared. And then I divide by omega. This will cancel with this omega, and I'll have 2 pi here. I'm sorry, kb cubed and dt. So now we have everything to calculate the loss factor for the composite system. So now the final result. And here we have, I'll use this equation.
Minus sign.
Minus sign, yeah. Just minus here, and then we have energy dissipation is also negative, they'll cancel out. Okay, so now we have this will equal to K B eta over 2 will equal to pi H2 G prime eta V gamma squared divided by 2 pi KB cubed D T W squared. And then I will substitute this here, and the result, this will give us eta will equal to of the constraining layer in terms of the eta of the viscoelastic damping material equal to H and this number is this number. G is equal to K1 and H2. And this is a very famous number, it's called the shear parameter. First, you could see from this equation that eta constraining has a maximum when partial eta constraining over partial G is equal to 0. And this is very easy, you can get it very directly for this case, will be at G is equal to 1. So now if you want to design constraining layer treatment and you want to get the maximum damping for this treatment, you set up G is equal to 1. Then this means you get relationship between the material property and this number. We wrote it down as E1, H1, and the geometry of the material, of the constraining layer. So this is the thickness of the viscoelastic. This is the longitudinal stiffness of the constraining layer. This is the wave number, and this is the shear modulus. G KB squared. KB squared. This is dimensionless number. Should be dimensionless number. Okay, also, this is one thing. The second thing is what is the physical meaning of this G? This is the equation, but we'll write it again. If W is equal to 0. So this means the constraining layer damping acts in longitudinal vibration. So the gamma now will equal to, if you remember, it was U1 minus U3 over H2 H Wx over H2. And what we've done so far, we said U3 is 0. And then also I'm sitting now, W is also 0. So this says that U and gamma are proportional to each other. Also from here, if I put W is equal to 0, then we have this equation. So this is ordinary differential equation, homogeneous, so it has a solution which is equal to gamma 0, the exponential, minus the square root of G asterisk over K1 H2 and X. Because gamma is proportional to U1, I can also rewrite this as U is equal to U0 exponential e to the minus G K1 H2 and X. Now if U0 over U, initially I have a large U, and then it becomes, I have a large U which is U0, and it becomes U, and I will say if this ratio is equal to the exponential E, then this equation becomes U0 over U will equal to exponential the square root of G asterisk K1 H2 and X. I flipped this equation. And then from here, this is equal to E. If this condition is satisfied, then I'm going to call this X, XE. Okay? Now if you look at the exponential here and here, is satisfied when the square root of G asterisk over K1 H2 XE is equal to 1, or XE squared will equal to G asterisk. I'm gonna take all this and plug it here. Then G will equal to, I'm gonna replace these three symbols by what we have. So this will equal to E squared. You'll see here but KB, which is the wave number. I can also write it down in terms of the wavelength. 2 pi over lambda b. And now G becomes equal to XE squared, and I'll replace this by what we have here. So this is lambda squared and 2 pi squared. And the physical meaning now of G is there's a ratio between the wavelength in bending and then this is defining the decay of the amplitude and the longitudinal direction along the constraining layer. So this is called the shear length. This is called the bending length. So this is ratio between the bending, the wave length, and the shear wave length. This is XE, and then this is lambda B. So now what we have to have optimum constraining layer performance, this number G should be 1, and these two should be compatible to each other. The bending and the shear should be very compatible to each other. If you are far from here and here, you will not have damping effectively because we will be way off at the ends of these two curves. Bottom line of all this, for constraining layer to work, we have to have balance between bending and shear. We have to have balance between these two numbers. Okay? So now what is left? Is the second case when U3 is not equal to 0. Okay, but this anyway give you a very good design criteria for designing constrained layer damping. We have to have this G is equal to 1 for optimum condition, and then you play with these parameters until you have the best optimum damping. Now, case B, when U3 is not equal to 0. Again, the starting point for this is the same as before. We have gamma is equal to U1 minus U3 H2 H over H2 Wx. I want to write U1 in terms of everything else. But before we do this, we'll come and say now here, if I come to this assembly and take a cross section anywhere, I have forces on the top layer, I have to have equilibrium of forces at any cross section. So I have to have forces here and the opposite direction. So if this is F1, this is F3, then sum of F1 plus F3 is equal to 0. And we'll say here, in the previous case, I put U3 is equal to 0. In this case now, U3 and U1 are not independent. They depend on each other because of this fact. Now we'll say here where U1 and U3 are dependent on each other. In order to have E1, H1, U1x, which is the force 1. Plus E3, H3, U3x is equal to 0, and this is F3. Then from here we can write down, I can write down this equation. We reduce it to K1 U1x, K3 U3x is equal to 0, where H3. So from here I can get the equation that U3 is equal to minus U1, K3 and K1. And then the rest is straightforward. So now I can take this and plug it in this equation. Then we have gamma will equal to U1. So I have 1 here. And then I have minus and minus, so it becomes a plus. K1 over K3 plus H over H2 Wx. Then I bring this to the left hand side. So I'll clean this, so this will be K1 plus K3, K3, H2, U1 will equal to gamma minus H over H2, H Wx. And then now U1 will equal to K2.
Still in the left hand side.
Okay, so let's make this later. H2.
And the left hand side should be eliminated.
I multiplied by
The
H2.
left hand side of the equation.
It should only be multiplied by the left hand side, the denominator.
The denominator, yes sir. The denominator. Okay. So now we'll have here U1 will equal to K3 H2 K1 plus K3 and gamma minus, same story, Wx. Then now I'm going to differentiate this 2 times, exactly as we did before. And then now replace this by F1. And now but partial. If you remember partial sigma 1 by partial x, times H1 is equal to the shear stress. This is for the equilibrium of this layer. The force times the area is equal to the shear stress times the area which is acting on. This is for equilibrium of top layer. This, again, is E1, U1 by H1. This was equal to G prime and gamma. And now I'll get this out. This would be K1. U1XX is equal to, we have the expression for U11 here. Then plug and get it as function of gamma. Then we have now K1, K3, K1 plus K3, and gamma XX minus K1, K3, H over K1 plus K3, WXX is equal to G prime and gamma, or gamma X will equal to H, sorry, bring this here. Huh? There's some H2 missing someplace.
Yeah.
Right.
XX. Lost your H2.
Huh? There's some H2 missing someplace.
Yeah.
Right.
XX.
This is correct. Okay. And then U1. So if multiplied by H2, this is correct. Gamma XX, yeah, we have the H2 here. Yes. Okay, now if we divide by H2, so we have this WXXX, H over H2, and then we have G prime and gamma, which is here now multiplied times K1 plus K3 divided by K1, K3, and H2. This equation is not too different from this equation, but exactly the same. Forget about this. This was the WXXX when we did the derivative. Okay, so this equation is exactly the same. The only difference is now instead of just the K1, I have the effect of K3. So now I have the effect of the bottom layer. So this is now the general case. I have the constraining layer, K1 parameter, constraining layer, the base structure parameter. Now, the solution, I'll just replace K1 by K1, K3. Get this, calculate the eta. Okay? So now, we'll just write down the final result. Then follow same procedure as case of U3 is equal to 0 to get eta constraint K1 h squared over dt. It's exactly the same, like this. And then here, this will be G over oops. So now what is left is in the homework is to make the top layer active layer. So we have the strain here, or the stress here is not this. The stress here will be this term minus the piezo strain, minus the piezo strain. If the piezo strain is equal to 0, it reduces to this case. Okay? We've done a fantastic job on the constraining layer now, like we covered it ins and out. So it has, I did the longitudinal case alone, complete. So you could see all the energy dissipation and the optimum length of the constraining layer. Maybe we'll just summarize this so we don't start the new section till next week. So what we've done, I did the longitudinal vibration. And the main purpose of all of this was to find the optimum length of the constraining layer. And this was following Plunkett and Lee paper. And we found L optimum over beta prime is equal to 3.28, and where the beta prime was the square root of G and E2, H1 and H2. So it has dimension of 1 over meter. So this is meter minus 1. Meter, this is called the characteristic length of the viscoelastic material. I'm sorry, 1 over characteristic length. So if you want to design an optimum length, that's how it is. Okay, and then so this is number 1. And then number 2, we used this to make a comparison between constrained layer damping and unconstrained layer damping. And we found from here that the energy dissipation for the unconstrained layer damping is much, much smaller than the energy dissipated in the constrained layer damping. And the reason is this was in tension and this was in shear. The viscoelastic material is in tension and this, the viscoelastic material, is in shear. Then number 3, we'll start looking at the transverse vibration. I did several definitions. Of the specific damping capacity. The loss factor, how the loss factor is related to the damping ratio. Through the equivalent viscous damping of a viscoelastic material. And then we did constrained layer damping with U3 is equal to 0. And then I found from this G shear modulus optimum, parameter. And then we showed that G is a measure or a ratio between bending and shear wavelength. And this says to have a successful damping treatment, you have balance between shear and bending. Optimality is ensured if there is balance between shear and bending. And then the last case, we did it for the general case when U3 is not equal to 0. Have a fantastic weekend. We'll see you next week. Kerwin's paper. This would be very nice. This section, I got it all from Kerwin's paper, which I think is volume 31, JASA, 1959. He has, if you can get hold of this guy's paper, these are fantastic papers to read. Okay, have a good day. will begin this topic. So far, what we've done, we looked at viscoelasticity, looked at shunted piezo networks, we looked at constrained layer damping. And in all these three topics, we either have a physical material that can damp the vibration, or we can have an electroactive material that can simulate this class of material. And here, this is an implementation or embodiment of how to use this material effectively in damping the vibration. So here we have a physical material. And here we have an electroactive material. I mean physical damping material. The material is intentionally designed and built for damping purposes. Here, this is electrically active material that I'm going to use it to simulate physical material. And then here is, as I said, is just a physical implementation of the viscoelastic damping. And in common in all these, we have energy dissipation. Okay, today we'll begin a new type of damping approach. Okay, this does not have either damping material or physically active material. It has no damping at all, but the performance of it looks like exactly like damping. So, so we'll say here periodic or aperiodic dampers attenuate vibration. But the key thing is without energy dissipation. What this means is we will redistribute the energy along the system, because the energy of the entire structure will remain the same because there's no energy dissipation, but I will redistribute it. So here, redistribute. The energy distribution, the spatial energy distribution.
spatial or harmonic?
What is this?
The
Excitation?
Is it the redistribution? Is it
Spatial.
spatial or harmonic?
On the space. And on the harmonic also. And on the harmonic. The space, we can do it with this. And on the harmonic, we can do it with this. Okay, so now, so maybe we'll just say here, distribute the energy spatially and spectrally, both in the space and frequency domain. In periodic dampers, they have unique characteristics. We'll say here rely on. Very important phenomena is called pass and stop bands. The aperiodic structures or aperiodic dampers these rely on a very important phenomena called localization. Okay, this looks like abstract so far, but for example, I can have a periodic structure of a damper that looks like this. Okay, this is all the same material, for example. And we know that this works because if you look at half of this, this looks like the car muffler. The car muffler, you come here from this end, you give high pressure fluctuation in the engine. And what comes out of the tailpipe is low pressure fluctuation wave. And the in-between, you use this change in geometry to attenuate the vibration or the acoustics from one place to another place. Now if I make many of these, I can have many mufflers. And then I can have large amplitude here, and at the output, I have very small amplitude. So spatially, I am redistributing the energy, and I am localizing it near the source of excitation. This is the source of excitation. How this works, we'll see how it works. But the main idea is you come and move in a medium. Let's say that this is one medium. And then suddenly you go in another medium. Because the area here is different than the area here, we have some mismatch. Exactly like when you have light flowing or passing through air and then it comes and hits the water surface. When it hits the water surface, the medium changes. Then I have reflection and I have transmission. If I design it properly, I can make this reflection comes with the incident wave and does destructive interference. Then I can reduce the amount of transmitted wave. If I design it properly, each one of these steps, I'll have this destructive interference. At the end, I have very low transmission of energy. The bottom line is, I have very high here, and then at the end, I have very low. So this is amplitude, for example, of pressure or of energy. And then this is space. So I'll have this characteristic. This characteristic looks like what you do is regular viscoelastic damper or regular shunted piezoelectric material. It does not have energy dissipation, but it looks like an attenuation. Okay? Now, here we have geometry discontinuity. But I can equally do the same by making this looks like this. And instead of geometry discontinuity, I'll have material discontinuity. So this can be material A, and then this is material B.
In that figure there, the amplitude versus space, is the amplitude increased in some areas to preserve the energy?
Of course. Originally this would be like this. Okay? But you will not see this from the beginning. If this is a straight pipe, that's what you will see. But once you put these restrictions, then the amplitude will rise in one place and attenuate in the other places.
So it increases at the source itself?
Yeah, concentrate at the source. Like for example, we're trying now to do, Dr. Pine and I, we are trying to do something like this. You have the helicopter, okay? And you have here your engine. And then you're mounting the engine on the airframe of the helicopter, okay? So you have gearbox, an engine system. And if you have these straight struts, energy will flow from the excitation source down to the airframe. Okay? But now I'm gonna come and instead of having these straight struts, I'm gonna make them like this. Okay? So once you do this, you concentrate the energy near the gearbox, which is already noisy. And you elevate all the vibration from transmission to the airframe where it affects acoustics and so on and so forth. Okay? So you can do this. Another example is if you have a torpedo. We're doing something like this for the Navy. You have a propeller at one end. You have guidance and control system on the other end. And in between, you come and put these periodic dampers. So by the time it leaves the propeller and it comes to the nose, all the energy is gone. The energy is concentrating here near the propeller, which is already noisy. And nothing goes to the nose where you have the guidance and controls and sensors and so on. Now, this is again for free. So don't expect a miracle. You cannot cut here and here, okay? You have to redistribute this characteristic, you redistribute it. And then you have high concentration here and lower here, okay? So now, for example, this other class, this is two materials, so we have here material discontinuity. And if you come and have sound wave propagating, it has sound speed. When it hits this, it has a different sound speed. So exactly like the ray of light going from air to water. So you have change in the boundaries, and you have what is called at this boundary impedance mismatch. Once you have an impedance mismatch, then you have reflection and transmission. If you design them properly, I can make the reflection and the transmission cancel each other. And you will see this when hopefully we get to it at the end of the day today. So now these are completely passive, completely passive. I can also come here and then now instead of just a completely passive system, I come and on the structure I come and bond piezoelectric material. For example, okay, this piezoelectric material, and I can use it completely in a passive mode, like the shunted network. Okay, so I have two effects. I have two effects. One of them because of the geometry change, and then the second I can have damping because of the piezo itself. Okay. Now this material can be piezo, can be shape memory material, can be anything, any active material. I can use what it looks to everyone like a periodic structure, which means this is exactly like this is exactly like this, the same geometry, everything is perfect. But when you manufacture any structure, it will have imperfection. 1 or 2 or 3%, as you will see, can change the dynamics considerably. So if you have machining imperfection, or if you have material imperfection, what it looks like a periodic structure becomes aperiodic. It is no longer periodic. And this has fantastic characteristics. Fantastic characteristics. So this, by its nature, localizes everything automatically near the source of the vibration. And I can have, instead of nice asymptotic decay like this, I can have almost like this. Very sharp decay. I localize everything here, relieve the entire structure from vibration. So now, if I use these as a shunted network, I can, in spite of the fact that these look periodic, I can come here on each of the shunted circuit, make the resistance here 1, make the resistance here 1.1, make the resistance here 0.9. So I am randomizing the resistances. So what it looks to me mechanically periodic, electrically it's not periodic, it is aperiodic. So now this structure will have these beautiful characteristics, as you will see. So if you depart from the conventional passive and try to augment the system with active component, I can intentionally introduce small or large aperiodic changes by adjusting the resistance very large, the inductance very large, and so on. You can play with these things without playing with the manufacturing of the shape. This is one advantage. The second advantage, as you will see when we analyze one of these, because it's completely passive, it will have this characteristic which is called also filtering characteristic. So I can generate here, for example, low pass filter, high pass filter, notch filter, or when I do the periodicity, I can make the low pass move, the boundaries of the low pass, the boundary of the high pass move, the boundary of the notch filter move. I can tune how big is the low pass, how big is the high pass or the notch filter. So you can tune this very easily because you can program the control gain that is associated with any one of these. Or you can leave, for example, 3 of them with no control and 1 with control. So you introduce aperiodicity. And you will see that the bands where we have wave propagating or they're passing, or bands that have no vibration motion, I can shift them. Okay? And the bottom line of this whole idea is people use control to attenuate the vibration. We will use control to stop the vibration. There will be no vibration. You select a 0 to 100, for example, hertz band, and in this band there will be no vibration. So this has tremendous power in many, many applications. So these are completely passive. These can be active, periodic, dampers, and then they have tunable, filtering, and attenuation characteristics. And the localization characteristics. What I was saying also, like when we analyze these systems, you will see that most of these passive systems are very good in attenuating high frequency vibration. Low frequency, they are not very good. Okay? And this is what we know in viscoelastic material. Viscoelastic is very good when you have high oscillation. When you have low oscillation, there will be very limited benefit from it. So these are exactly the same. At low frequency, they don't have enough power to do the filtering characteristic. But at high frequency, they are. Now, if we introduce active component or a periodic component, I can shift the performance to low frequency. To low frequency. For example, if you have the torpedo application that I'm saying, and you have vibration in around maybe 100 hertz, you need the torpedo to be almost half a mile, so you can get the benefit of the attenuation. Okay? But if I put active component in it, I can make it very small, so you can get the benefit of it. Okay? Saeed's thesis will be on this topic, and he's done a lot of work on, like in this area. So it has many directions that you can think of. The application are just limited by our imagination. I'll begin by looking at simple cases first, and then we will go into rods again in this class. So again, this system to analyze it, I can come, for example, and I say this system looks like it is made of unit cell, like this. And this cell is is repeating itself along the structure. In this example, I'm repeating myself only in one dimension, but I can repeat myself in 2 dimensions in case of plates, and in 3 dimensions in case of shells. Okay, this is one representation, or I can see the same structure is made of cells that looks like this. That repeat themselves also along the structure. This is called asymmetric shell. In spite of the fact that it is symmetric, the matrices look slightly bad, but they are much better than these matrices. Okay, because these matrices I have to do finite element for this, finite element for this, and then finite element for this. So I have to have assembly of 3 matrices. Here I have assembly of only 2 matrices. They are simple, but these, when you write down the final matrices, they become beautiful. In spite of the fact that they are very complicated to begin with, the off-diagonal elements become 0. So these called asymmetric. These are called symmetric matrices. Symmetric cells. Okay, and I can take these and, for example, do them like this. I can take the periodic structure and divide it into black boxes like this. This is one black box connected to the second box, and so on. So this is cell I plus 1, and then cell I minus 1. In the first simple case that we have, which is one-dimensional elements, I can, for example, this is cell I. I have here node, and I have here another node. And I'm going to call this node the left, and I'm going to call this node the right. So this is left and right. And the same thing for other cells, left and right. Okay. So for 1D systems, I can write the equation of motion like this. Again, I don't have damping in here in this system. So I have one-dimensional system. We write down the displacement of the left node. the displacement of the right node, the displacement dot, double dot, and the displacement double dot. So this is the mass and the stiffness matrices. And I'll just, for this first one-dimensional case, I can take this as a rod, for example. Because the beam also is one-dimensional case, but the matrices will be 4. Okay, so now the mass matrix will look like this, M, and I'm going to write him like this, M11, M12, M21, M22. And then the same here, K11, K12, K21, K22. And then the final result is here, force on the left, force on the right. If we have sinusoidal motion, then now I have like this. And this would be K11 minus M11 omega squared, and so on. K12, M12, M capital, K21 minus M21 omega squared, omega squared. And we can write this like this. And I write it in this form, K, LL, KLR, KRL, KRR. And the reason is this matrix is called now dynamic stiffness matrix. So now the final result that we have this. All of us can generate this matrix because this, for any system, no matter how it looks, either geometry discontinuity or material discontinuity, we can write the finite element for this, assemble these two matrices. So we can generate the mass matrix and the stiffness matrix, and then combine them to generate the dynamic stiffness matrix. Now if you look here, you will see this. We have on this side deflections, and on this side forces. I'm going to reshuffle these equations. So I'm going to have here forces and deflection, and here I have forces and deflection. This on the right, this is on the left. So now I can write the top equation, expand. I'll have FL PLL UL KLR and and UR. Or UR, and I'll multiply by the inverse of KLR, or the reciprocal, because these are scalar, but if you have bigger matrices, then these can be matrices instead of scalar, and we can multiply by the inverse. So this will equal to FL, KLR, inverse, and then I move this to the right hand side, so this becomes KLR inverse, KLL, UL. Okay, now the second equation. It is FR is equal to KRL UL plus KRR UR. I'm going to replace UR from here. So this will equal to KRL plus minus KLR inverse KLL KLR inverse and FL. And I'll group the UL terms, and I'll group the FL terms. So I have here KRR, KLR inverse, and then I have here three terms, KRL, and then I have minus KRR, KRLR inverse, and KLL. And of course, one important thing is these two are the same, because any stiffness matrix is symmetric. So KLR is equal to KRL. Okay. Now, if you look at this equation and this equation, what we have, if I put them in a matrix form, I have deflection on the right, the force on the right, and then I put these two equations in a matrix form. So I have U on the left, F on the left. So now this can be written in a matrix form like this. U right, F right is equal to KL right inverse, U left, F left. And then we have from here minus KLR inverse, KLL, KRR, K inverse, LR, and then KRL minus KRR, KLR, and KLL. Now I'm going to do one more thing. First, this vector is the displacement and the force on the right cell I. and the other vector is on the left of the same cell. So I'm going to put here cell I and cell I. If I come and look at this interface between cell I and cell I plus 1, this is a continuous medium. Continuous medium. So the displacement here is exactly the displacement here. So this means I have to have U R of cell I is equal to U left of cell I plus 1. This is compatibility of displacement. At the same time, the force here and the force here have to be in equilibrium. So I have to have the two, sum of them is 0. So I have force right at I is equal to minus the force left at I plus 1. Now I'm going to take these conditions and put them here. So now UR at I is equal to UR at I plus 1. The force at I is equal to the negative of the force at I plus 1. Okay, and then the rest is the same. This will be KLR inverse. Now, instead of leaving this negative here, I'm going to take this negative out and multiply the rho by negative. So I'm going to remove this out. And then I have here minus. And then here will be minus. KLL. Now this has a beautiful assembly now. The vector of U and F here in one cell is related to the vector U and L of the following cell. Now, if I want vibration to attenuate, so this vector has to be greater than this vector. And we will find the condition that will make this vector greater than this vector. If the two vectors are the same, everything that goes in will come out. And you will see this if I have a straight rod and I make the equation of it in this form, you will see that what comes in will equal exactly what comes out. So everything will propagate. Now, this matrix has a very famous name. It's called the transfer matrix because it takes the input state vector and transfer it to the output state vector. So the input at the cell I, the output at the following cell I plus 1. So this is called my transfer matrix. This matrix, I wrote it down for the rod. It will be exactly the same for the beam. But these, instead of 1 by 1 by 1, will be 2 by 2 matrices. So I'll have 4 by 4 matrices. Okay? Now, this vector is called the state vector. Y at I plus 1. And this is my state vector at I. The transfer matrix is given the symbol cap T. And this reduces to y I plus 1 is equal to T, y, and I. This is a matrix. I can write this matrix like this. If I have a matrix and I'm multiplying it by a vector and I put the vector here, so this number is the eigenvalue of this matrix. Eigenvalue of this matrix. Now I'm going to combine these two equations. This is by definition. This is by the analysis. So you analyze the system, any system. Rods, beams, plates, shells, you will end up with the same equation, the same form. And this now is reduced to conventional eigenvalue form like this. Now I'm combining these two equations and I'll eliminate these two terms. So the result will be y I plus 1 is equal to lambda y I. And here it's very easy now to see if the absolute value of lambda is equal to 1, output is equal to the input. If the absolute value is less, then the output will be attenuated by the value of lambda. Now, before we do this, well, the matrix, this dynamic stiffness matrix, as you name them, KLL, KLR, KRL, KRR, you take it from the finite element description and you cast it in this form. So once we have this, then we get the matrix T. And I'll just look here at the basic characteristics. Of the transfer matrix T. First item, let's look at the determinant of T. If you look here, the determinant of T, KLR, KLL, KRR, KLR, and this is positive. And then minus KLR inverse times KRR, KLR inverse, KLL. So this term is duplicated exactly here, and the negative of it they cancel. This term, KRL, this term is the inverse of it. So the multiplication is 1 and we have minus, so it becomes 1. So this class of matrices, their determinant is equal to 1. Okay? And we'll just say, just expand T, okay, to get the proof. In the case of beams, this is 4 by 4 matrix. The result will be identity, its determinant is equal to 1. Now here, I'll just make here a little note. T inverse transpose is equal to J T J inverse, where J is equal to 0, 1, minus 1, and 0. In the case of the rods, in case of beams, 0I, 2 by 2, I, 2 by 2. The proof is very easy. You just take the T, multiply it by these two, and then you can prove this is equal to this. And the easy way of doing it, we'll say here, let T is equal to and then just perform check above identity. Why is this? Because of this characteristic. Number 2, and I'll leave the title free for a minute. We have here T, Yi is equal to lambda Yi. So I'm going to rewrite this like this. T, Yi, and I'll come and multiply here by J and here by J. And in the middle here, I'll put J inverse and J. So these two are identity matrix. This is right here. Now I'm going to group these. I'm going to call this Xi, Xi. This matrix now I can replace it from here. So this will be T inverse transpose. I'm going to multiply this last equation by T transpose, So this will be identity Xi, and I'm going to take this lambda and bring it here. And then I have Xi here, and then I will multiply it by T transpose, so T transpose will appear here. So I want you to look at this equation. And this equation. What can we say about the matrix T? Orthogonal? No. Matrix. T has eigenvalue lambda. If I put this T transpose, what would be the eigenvalue of T transpose? Lambda also, right? But here we have T transpose, its eigenvalue is 1 over lambda. So these matrices have eigenvalues that appear in pairs, reciprocal of each other. So matrix T has eigenvalues in pairs, lambda and 1 over lambda. Okay. Now what is this? If I take a rod and then give it a wave propagation in it, the wave will have propagation in the positive direction and in the negative direction. In the positive direction and the negative direction. So these are corresponding to these two eigenvalues. These two eigenvalues. Because I can rewrite this lambda like e to the power mu. So this eigenvalue will be e to the minus mu. So I have propagation in the negative and the positive direction. And we'll see this when we get to the end. Because we will take the matrix, transfer matrix, and then if we do diagonalization on this matrix, you will see I have wave propagating in one direction, wave propagating in the opposite direction. And this matrix will have off-diagonal elements zeros, unless we come and make the structure periodic. So the off-diagonal elements will not be zero. And that's very important key to localize the vibration at one location. Okay, so the bottom line now of this, this matrix has unique characteristics. Determinant is unity, and this is super important. All the eigenvalues appear in pairs. Each pair is the reciprocal of the other. In the beam, I'll have 4 eigenvalues. 2 in one pair, 2 in another pair. And we know this, if I write down the equation of wave propagation in a beam, I know one of them is ik, one is minus ik. One is k, and one is minus k. So they appear in pairs. And the pairs are reciprocal of each other. Okay. We'll write down a couple more, we still have plenty of time. And we'll just say here a little note here. Again, we have T is equal to then the characteristic equation of this system is again lambda I minus T is equal to 0, or lambda minus T11, T12, T21, lambda minus T22 is equal to 0. Now we expand. When we expand, we'll have lambda minus T11, lambda minus T22 plus T21, T12 is equal to 0. So from here we have lambda squared.
Minus. That should be minus T21, T12.
Yeah, sorry. Okay, so we have minus T11, T22, lambda, and then plus T11, T22, minus T21, T12 is equal to 0. Now if we look at this last a group of terms. Last group of terms is this times this minus this times this, which is the determinant, which is 1. Then what we can say now, for example, if x squared minus 5x plus 6 is equal to 0. So this says that I have x minus 3, x minus 2 is equal to 0, and the roots are 2 plus 3. 2 plus 3 is this number, okay? So the sum of the roots is the second term, this polynomial. So this says now, then lambda plus 1 over lambda is equal to E22. Okay? Now we have everything. You know, like we have this from the finite element. Okay? Then automatically I can get lambda and lambda 1 from here. Okay? And we'll say now here, if, as I did at the end of the last board, if lambda, I put it equal to e to the mu, and of course 1 over lambda will be equal to e to the minus mu, then lambda plus 1 over lambda is equal to e to the nu, e to the minus mu, which is equal to twice cosine mu. Then now T11 plus T22 over 2 is equal to cosine mu, or mu is equal to cosine inverse 1/2 this parameter is a very important parameter, and it is called propagation parameter. Why? Again, state vector is equal to lambda y I. I'm going to replace each lambda by e to the mu yi plus 1. Then I can have, for example, a case like this. This e is equal to a real part plus an imaginary part. I can break it down to like this, e to the alpha yi, and then e to the I beta. I can have cases where alpha is equal to 0. So this absolute value of this number, because I can expand it to cosine plus I sine, absolute value is equal to 1. Equal to 1. So if alpha is equal to 0, this will equal to this. And that's what you will see in propagation and rods. I have this term will be sine and cosine, its magnitude is unity. Now, if I don't have beta, and I only have alpha, e to the alpha, it is a decay parameter, so I attenuate the output by multiplying it by this, exponentially decaying function, and the input is attenuated. So now from the propagation constant, I can break down two pieces, alpha, and this is called the attenuation parameter. Beta will be a phase shift parameter. And we'll see its value when we get to the examples. So here is called attenuation parameter. And then beta is called the phase shift parameter. Okay, so now we're in good shape to do examples, and we'll do them next time. Have a good evening. Maybe I'll just give you the handout so I don't take it with me. This handout is on a spring mass system.